Good afternoon. My name is Ilya Sevastyanov, and I'm glad to present you our report titled Study of Structural Feature cuprum 1 - X palladium X ferrum sulfur 2 compounds. The study of thermoelectrical materials has been of interest recently. It was proposed to use magnetic semiconductors. The cuprum ferrum sulfur 2 semiconductors compound belong to this type of compounds. Thermoelectric and transport properties of samples of the cuprum 1 - X palladium X ferrum sulfur 2 structure, X equal 0 to 0.1 were shown. In this paper, we present the results of a study of a series compounds cuprum 1 - X palladium X ferrum sulfur 2, X equal 0, 0.01, 0.02 in comparison with the structure of cuprum 1.02 ferrum 0.98 sulfur 2 by NMR 6365 cuprum in the local fields and EPR methods. Semiconducting chalcopyrite with a tetragonal structure has been recently studied as a potential candidate for thermoelectric application. In the present study, palladium substitution for cuprum was designed in terms of thermoelectric properties. A series of undoped chalcopyrite and palladium doped chalcopyrite were synthesized. The thermoelectric and transport properties of hot pressure sample pairs were characterized before. The spectral parameters of 6365 cuprum NMR in the local fields in chalcopyrite were measured, and TechMark redstone multiples NQR NMR spectrometer measure of the NMR line shape was performed using quadrate detection by recording spin echo signal with step-by-step passage of the frequency range and signal accumulation. The EPR spectra and doped chalcopyrite and palladium doped chalcopyrite were studied on a Bruker stationary X-ray spectrometer ESP 300 in the temperature range 15 to the 300 Kelvin. The masses of the sample were approximately the same. Polycrystalline sample with a nominal composition of doped chalcopyrite and palladium doped chalcopyrite were synthesized from a mixture of pure elements obtained from sigma Eldridge, including cuprum, palladium, ferrum, and sulfur. The synthesis of the polycrystalline products were performed in evacuated and sealed quartz ampoules. The ampoules were heated up to 1223 Kelvin over 10 hours, maintained at this temperature for 24 hours, and then slowly cooled to room temperature. The resulting ingot was then ground under acetone, pelletized, and annealed at 923 Kelvin for 24 hours. Then it was slowly cooled down to 673 Kelvin and then cooled to room temperature by switching off the furnace. The result of EPR experiments are present in figures. The behavior of spectra of sample of composition cuprum 1 - X palladium X ferrum sulfur 2, X equals 0.01, 0.02 is compared with the spectrum of the sample cuprum 1.02, ferrum 0.98, sulfur 2. Distinctive feature of the cuprum ferrum sulfur 2 sample in the presence of an intense EPR signal with a wide anisotropic line shape over the entire range of the studied temperature, presumably having a ferromagnetic nature. Also in the temperature range of 100 Kelvin to 130 Kelvin, there is a rapid change in the signal parameters, which indicated the possible presence of a structural phase transition. A distinctive feature of the EPR spectra of the cuprum 1.02 ferrum 0.98 sulfur 2 sample is almost complete absence of an intense signal of ferromagnetic nature in the entire range of temperature studied. At a low temperature, a signal with a G factor of G equal 2.08 is clearly visible. Its intensity and the shape of the line change as it heat up to the room temperature. 6365 cuprum NMR spectra of the cuprum 1.02 ferrum 0.98 sulfur 2 sample figure have a structure similar to that of the cuprum 1 minus X palladium X ferrum sulfur 2, X equal 0.01, 0.02, and cuprum ferrum sulfur 2 samples. Each line of the Hildebrand spectrum of the on the high frequency side is complemented by a white line at smaller amplitude, and the main lines of Hildebrand are widened and not symmetrical and slightly shift to the high frequency region of the spectrum. The main figure of the spectrum of the sample cuprum 1.02 ferrum 0.98 sulfur 2 is a closed correspondence to the spectrum of Hildebrand. The above mentioned effects of broadening and displacement of line are minimal in study group of samples. Conclusions: EPI and NMR studies of the feature of the cuprum 1.02 ferrum 0.98 sulfur 2 sample show its lower effects compared to the composition of Hildebrand, and the effect of this structure on the spectra is similar to samples of the cuprum 0.99 palladium 0.01 ferrum sulfur 2 structure. The results of EPI and NMR studies also show that the composition of Hildebrand is not a stoichiometric composition of Hildebrand, but it's a stoichiometric Hildebrand with structural defects. A rapid change of the shape of the EPR spectrum was detected in the temperature range of 100 Kelvin to 130 Kelvin in the Hildebrand sample, which presumably correspond to a possible structural phase transition. We have previously shown that the natural Hildebrand does not have a phase transition. All this result may also indicate that the cuprum ferrum sulfur 2 formula is not stoichiometric for Hildebrand. The broadening of the NMR resonance lines may be the result of the increase in the number of defects in the critical lattice of the compound, leading to a large spread of EFG of the resonant copper nuclei. Such defects can be ferrum cuprum 2+ anti-side defects. The formation of such defects is caused by the formation of the palladium sulfur phase in the Hildebrand matrix with increasing nominal content of palladium. Thank you for your attention.
Thank you very much for your presentation. Somebody have some questions? I cannot see any questions, so I have a question which is very simple, but nevertheless, on the spectra with on the slide with NMR spectra, you have next maybe appears now this one at 50K. The spectrum contains some unusual lines, additional lines with bigger field on the right of the slide, on the right. What is the origin? This is some kind of additional signals, real signals, or what is this?
We think it's anti-side defects, some defects, maybe.
Maybe, yeah. Okay, thank you very much.